Now, coming to next topic, that is pin diagram of 8085. So we have discussed it earlier also that total pins in 8085 are 40. 8085 is made up of total 40 pins. So see, what we are going to do is that we are not going to discuss all the 40 pins of 8085 at one go, because if we do it, then you will not remember each pin of 8085 and it will just get messed up. So what we will do is that we will form different groups of pins of 8085, and then we will discuss each group in detail. We will discuss sub parts of those groups in details. So till the time we complete this course, all the 40 pins will be discussed by me in details, covering all the aspects and all the concepts. And you will also get comfortable with all the pins, and all the pins will be on your tips. So if any question is asked in question, if it is objective, then you can easily solve it. And if it is subjective, that is, if this question is asked in ESE, that draw pin diagram of 8085 and brief it, then you will become so comfortable with it that this will be the first question that you will attempt in your exam. So let's start it. So the first group which I have formed is that first we will discuss about this address bus, that is um, A15 to A8, that is pin number 28 to 21. Along with it, we will discuss this address cum data bus. It is represented by pin number 12 to 19. And then we will discuss control signals like read bar, write bar, and we will also discuss some status signals like input output, memory bar, S1 and S2. So this is my first group. I am going to discuss this all pins in details as a first group, and then we will continue with the other pins of 8085 microprocessor. So first we will discuss about address bus, data bus, and control bus. And then we will look into control signals. Then we will also look into status signals. And then in the later part, we will see that how multiplexing is done in a microprocessor. And the same bus which acts as an address bus, it also acts as a data bus. So we will discuss all this concept in details, and it will be very interesting. You will really enjoy it. So if we talk about the higher order address bus, then what we all are going to discuss, we will discuss A15 to A8. These are known as higher order address bus. These are known as the higher order address bus, higher order, higher order address bus, higher order address bus. See, these all pins are not complete pins of 8085. I have just taken the first group, which I told you earlier that in the first group we will discuss address bus, data bus, control bus, and control signals and status signals. So this is our higher order address bus. Let's suppose this is our lower order address bus, AD7. Why we are denoting it as AD7 to AD0, that I will discuss in details in later part. But for the time being, you just note it down that lower order address bus also act like a data bus. So A for address, D for data. So it is noted as AD7 to AD0. Suppose we write it as lower order address bus. Lower order address bus. This all we will discuss in details. The multiplexing part I am going to discuss in details, and I will give you a very important concept, and I will try to make it very simple for you, and you will really enjoy it. That part, which we will take shortly. Address bus. Then we will discuss about some control signals like read bar, write bar, ALE. ALE is address latch enable. We will discuss in details its working. Then we will discuss some status signals like S1, S0. We can add one more here, input output memory bar. So this all pins we are going to discuss in details. Um, we will come into it. Let me first complete it. I will brief this diagram to you in details. Don't worry. Suppose this is my address bus. This is my address bus. This is my data bus. This is my control bus. Control bus. I will come back to this diagram, but first we will discuss address bus. So we have discussed it before also, that the addresses, be it for input device, be it for output device, be it for memory, addresses are always generated from the microprocessor for peripheral devices. Addresses are always generated from microprocessor for peripheral devices. So we can define it. Address bus is used to transfer the address of either memory of input output device from the processor. It means address of input output device or address of memory is always originated from the microprocessor. So as I am saying that address are originated from microprocessor, so we can say that address bus are unidirectional. Important. This all questions frequently comes in objective exams. So what I am saying is that addresses are always generated from microprocessor. So address bus are unidirectional. Address bus are unidirectional. Address bus are unidirectional. Okay. Now come into this diagram. So as I am saying that address bus are unidirectional. So this. So what will be the direction of arrow for address bus? It will be here. That is microprocessor is originating an address for input device. Similarly, address of output device is originated from 8085 microprocessor. Similarly, address for memory is originated from the microprocessor. So we can see that address bus is always unidirectional. Address bus is always unidirectional and it is pointed from microprocessor for peripheral devices. From microprocessor for peripheral devices. Okay. Now coming to other aspects of address bus. If we talk about 8085, then 8085 there are total 16 address line or we can say there are total 16 address bus. 8085 has total 16 address bus. Now see, there is a one very important relation between address line or address bus and the memory connected with it. We can write it as this: 2 to the power n is equal to n. 2 to the power small n is equal to big N. Here small n is number of address line or number of address bus. Big N is number of addresses or memory locations or registers required or connected with the microprocessor. So suppose we are saying that in 8085 there are total 16 address bus. So we can write it like this: 2 to the power 16. We discussed it in number system also, where I told you that one figure will be very important for you in future, and now we are going to see that figure. So 2 to the power 16, it will come to be 64 kilobyte, 64 kilobyte, and this figure will come as 65536. So what is this 65536? 65536 is the total number of memory which can be connected with microprocessor 8085. It is total number of memory which can be connected with microprocessor 8085. So if we have the knowledge of address bus, if we have the knowledge of address bus, that how many address bus or address lines are there for any processor, then how many memory can be attached to it, how many memory locations, how many memory locations can be attached to it, we can easily find it out. We can easily find it out. We can easily find it out. So I think this is clear to you. So from the so we can conclude one thing, that from address line, from address, from address line or address bus, we can conclude, we can conclude total memory locations, total memory locations, total memory locations available or connected with the processor, available, available or connected with processor, or connected with processor, or connected with processor. So this is an important conclusion you should remember. So if we talk about address bus, then addresses are always originated from processor for peripheral devices. That's why address bus is always unidirectional. If we talk about 8085 microprocessor, then it has total 16 address bus or 16 address line. So total number of memory locations which are connected with processor, that we can find it out from a simple formula, that is 2 to the power small n is equal to big N, where small n is equal to number of address line and big N is the number of memory locations which can be connected with the processor. And same we can say that how many registers are also required, that also we can calculate it from the same formula. The memory locations, registers, addresses, number of addresses, all are same, all are same. So now let's take some question based on that formula. So here what it is said: a processor has 24 address lines. Calculate maximum memory that can be connected. So we very well know the formula, that 2 to the power n is equal to big N, where small n is total number of address line and n is total number of memory locations connected. So in the question it is given the total number of address line is 24 and we have to calculate maximum memory that can be connected. So what it will be, we can write it like this: 2 to the power 4, 2 to the power 20. We can write it like this: 16. 2 to the power 10, I told you, is 1 kilobyte, and 2 to the power 20 is 1 megabyte. So it will be 16 megabyte. So 16 megabyte memory can be connected with this processor having 24 address line. I think it is easy, simple formula. Max memory connected. Max memory connected. Now, if we take another example, a memory of itna terabyte can be connected to a process, find number of address line. So if we write the formula 2 to the power n is equal to big N. So here big N is given, that is total number of memory locations which are connected. It is given, that is 256 terabyte, and we have to find number of address line. So we can write it easily: 2 to the power n is equal to 256 terabyte. This we can write it as 2 to the power 8. Terabyte is 2 to the power 40. We discussed it earlier also. So it will become 2 to the power 48. So n, that is number of address line, will be equal to n, that is number of address line, will be equal to 48. This will be our answer. Easy. Now coming to another question. Here also total number of memory which are connected with microprocessor is given 100 gigabyte. Now we have to calculate number of address line. So we very well know the formula: 2 to the power n is equal to big N. Okay. So now So now 100 gigabyte, 100 gigabyte, gigabyte can be written as 2 to the power 30, 2 to the power 10 kilobyte, 2 to the power 20 megabyte, 2 to the power 30 gigabyte, 2 to the power 40 terabyte. So see, here we have two options. 100, that is if we take 2 to the power 6 into 2 to the power 30, then 2 to the power 6 will be, it will be 64, it will be 64 gigabyte, it will be 64 gigabyte, 2 to the power 36, it will be 64 gigabyte. And another option is that if we will take 2 to the power 7, 2 to the power 30, then 2 to the power 37, it will be 128 gigabyte. So now you will get a confusion that which one to choose. If we are taking 2 to the power 6, then we are getting 64 gigabyte, which is less than 100 gigabyte. And if we are choosing 2 to the power 7, then we are getting 128 gigabyte, which is greater than 100 gigabyte. Then what will be our answer? So our answer will be this one, that is 128 gigabyte, and the number of address line will be n is equal to 37, because we can afford to have some empty spaces, but we cannot afford to lose data. But we cannot afford to lose data. Here, if we will take 64 gigabyte, which is less than 100 gigabyte, then we will lose data. Here, if we will take 128 gigabyte, which is greater than 100 gigabyte, then we will have some empty spaces. But it is better to, but we will not lose any data. So it is better to have empty spaces than to lose data. So I hope this question is clear to you. Fine. Now coming to the next bus, and that is data bus. So data bus has multiple role. Data bus has multiple role. It is used to transfer data between microprocessor, memory, and input-output device. See, first let's the second this point also. Data bus is bidirectional. This is important. In address bus, we saw that address bus is unidirectional, but data bus is bidirectional. See, this point, that why data bus is said to be bidirectional. This I am going to discuss shortly when I will discuss multiplexing of address and data bus, and there I will take it there I will take you in depth that what exactly happens in microprocessor, how multiplexing is done in microprocessor, and why data bus is acting as a bidirectional. That there I will discuss in details, but here you just remember that what is the role of data bus. See, I told you that total address line in 8085 microprocessor is 16. So we write it as like this, that is A15 to A8, and then A7 to A0, A7 to A0. This I told you that this is our higher order address line, and this is our lower order address line. Then see, this lower order address line can also be used as a data line. That's why we also denote it as AD7 to AD0. So what happens is that at one instant, this lower order address line, it act as a address line, and what it does is that it take addresses from microprocessor, and then it gives it to input devices, output devices, memory. That is, it is acting like an address line. Then again, in second instant, this data bus will change its role. And now it will bring data from input devices, from output devices, from memory to the microprocessor. So data bus is doing multitasking, I will not say data bus. I will say that this lower order address bus is doing multitasking. At one instant, it is acting like an address bus, where it is taking addresses from microprocessor, and then assigning it to input, output, and memory devices. And then in the second instant, it is taking data from the peripheral devices and bringing it back to microprocessor. That's why data bus is said to be bidirectional. Because it is doing multi role. At one instant, it is acting like a address bus, and in second instant, it is acting like a data bus. How it is exactly happening inside the microprocessor, that I will discuss in detail, and you will really enjoy that part. But for the time being, just keep it in mind that data bus is used to transfer data between microprocessor, memory, and input output device. Okay. Here data means address and data both. That depends that in which role data bus is acting, whether it is acting like an lower order address bus or it is acting like an data bus. It is bidirectional. Now it is important. We discussed earlier also that 8085 is a 8-bit microprocessor. 8085 is a 8-bit microprocessor. Why it is called 8-bit microprocessor? It is called 8-bit microprocessor because total number of data lines or total number of data bus which is available in microprocessor, it is 8-bit, is 8-bit, is 8-bit. And here I have written it clearly that a processor is identified by the length of a data bus, that is number of bits it can process at a time. That is, if we are calling 8085 as a 8-bit microprocessor, then after learning this concept, if anyone asks you that 8085 is called 8-bit microprocessor, then why it is so? Then you will directly say that it is called 8-bit microprocessor because it has 8 data lines. It has 8 data lines. Suppose we have another microprocessor, XYZ microprocessor, and if someone tells you that XYZ microprocessor is a 50-pin microprocessor, XYZ microprocessor is 50-pin microprocessor, then tell me how many data lines or how many data bus is available in XYZ microprocessor. Then you will simply say that there are 50 data lines or data bus. That's why it is known as a 50-bit microprocessor. So I think this part is clear. Data bus, it is bidirectional because at one instant it act like an address bus and in second instant it act like a data bus. And in 8085 they are total 8-bit, they are total 8 data lines or 8 data bus. That is why we are calling it as 8-bit microprocessor. And from the number of data lines and number of data bus, the length or the bit of microprocessor is defined. So I can conclude here one thing, that if we have an idea, that if we have an idea of address line or bus, if we have an idea of address line or bus, then if we have idea of address line and bus, if we have idea of address line and bus, then we can conclude total we can conclude total memory location. We can conclude total memory location. We can conclude total memory location attached with microprocessor. We can conclude total memory location attached with microprocessor. And if we have an idea of a data line or data bus, then we can conclude length of microprocessor. Then we can conclude length of microprocessor. Then we can conclude length of microprocessor. This is important. This is important. Now, coming to the third category of bus, and that is control bus. So what is control bus? So control bus is used to transfer the control signals required for various operation of the processor. So it is used to transfer the control signals and clocks. We can also write control signals and clocks required for various operation of processor. Some of the examples of control signals are ALE, address latch enable, read bar and write bar. Read bar and write bar. See here, we generally get two type of confusion. One is we get confused between control signals and status signals. That which one is control signals and which one is status signal, we get confused with that. So I told you that ALE, read bar and write bar, these are our control signals. And if we talk about the status signals, and if we talk about status signals, then status signals are S1, S0, input output, memory bar. These are our status signals. See, this ALE, read bar, write bar, S1, S0, input output, memory bar, we are going to discuss in details. Don't worry about it. Here we are just defining some things. So I am telling that control signals are three: ALE, read bar, write bar. Status signals are S1, S0, input output, memory bar. Generally the confusion is regarding this. Many times student confuses that this is the control signal and they do mistake in exam. Okay. Then the second confusion is that whether control bus is unidirectional or bidirectional or partially bidirectional or partially bidirectional. We get confusion here that whether control bus is unidirectional, bidirectional or it is partially bidirectional. Then see, if you are given a question like this, control bus are option A uni, option B bi, option C both. And we have another question. Control bus are, also write this. No. Here control bus are uni, bi, partially bidirectional, D is none. So if you get a question like this, then our correct answer is unidirectional. Keep it in mind. It is unidirectional. But if we have a option which is partially bidirectional, then this will be our answer. I am telling that if you get a question like this where you have uni, bi, both none, but you don't have any option regarding partially bidirectional, then go for uni. Don't go for none because uni is given. Don't go for none because uni is given. Go for uni. But if you are given a question like this where it is mentioned that it is partially bidirectional, then go for C. Okay. Now, why I am saying that it is partially bidirectional? So coming back to our this diagram. Then see, this is our control bus. What is the function of control bus? It is to take control signals from microprocessor and then give it to input, output and memory. For direction sake, I am showing it as unidirectional. For the direction sake, I am taking it as unidirectional, but it is partially bidirectional. Why it is partially bidirectional? Because after taking control from microprocessor to the peripheral devices, it also gives a confirmation message to 8085. It also gives a confirmation message to 8085. That's why we are calling it as partially bidirectional. That's why we are calling it as partially bidirectional, because it sends a confirmation message to 8085 after it has communicated with peripheral devices. So I hope this is clear to you. So now we will come to multiplexing of addresses and data lines. So see students, till now what we have discussed is that we have discussed some terms, and we have discussed many theory concepts, many theory things we have seen. Now we are going to come into the execution part. Now we are going to deal with the execution part, that how exactly instructions are executed in microprocessor. So now things will become very interesting. I'm going to give you number of shortcuts, number of important concepts, and you will have an insight of how microprocessor is actually working. So things are going to become very interesting from now onwards. So just listen to me carefully. Now, coming to next topic, that is multiplexing of address and data lines. Very important topic, very interesting topic, and from here onwards, we will get a look, or we will get an insight of how microprocessor actually works. So please listen it carefully. So first of all, I will try to uh, tell you that what is our overall aim. Our overall aim is that suppose we have a memory. Suppose we have a memory. Address of memory is suppose address of address of memory is suppose 2060H. Okay, we have a memory, and the address of this memory location is 2060H. Now microprocessor wants to communicate with this memory, read data which is present in this memory, and then bring that data back into the processor. So basically the aim of microprocessor is reading data from a memory having memory location address as 2060H. So basically what microprocessor want is that it wants to read data present at memory locations 2060H. This is the final aim of microprocessor. We are just taking an example so that we can see that how microprocessor actually works, and how basically how multiplexing is done in between address and data lines. So here this is our memory location, this is our decoder. See the functionality of decoder and memory location we will see in details in coming session, but here just you remember that this is memory location, this is decoder. For time being, you just keep in mind that the what is the function of decoder. It is acting as an interface between memory and microprocessor. Microprocessor doesn't communicate with memory directly, it communicates with memory through a decoder. Okay, it is fine. Then here we are having a latch, here we are having a latch, here we are having a latch. This module is called a latch. It is an external module which is connected with the microprocessor. It is an external module which is connected with a microprocessor. So what all we have seen? We have seen that we are having a memory location whose address is 2060H. we are having a decoder which is acting as an interface between microprocessor and memory, because microprocessor doesn't directly communicate with memory, it communicates with memory through decoder. Then we are having a latch which is an external memory, which is an external module connected with the microprocessor. And what this latch is containing, this latch is containing D flip-flops. This latch is containing D flip-flop. This latch is containing 8 D flip-flops. This latch is containing 8 D flip-flops. This latch is containing 8 D flip-flops. Then what was our aim? Our aim was that microprocessor wants to communicate with memory location having address 2060H, and it wants to read data which is present in this memory location having address 2060H. Fine. Now see, we discussed it earlier also that there are total 16 address line. There are total 16 address line which we denoted as A15 to A8. This is known as our higher order address line, and then A7 to A0. This was called as our lower order address line. This was called as our lower order address line. We also discussed that there are total 8 data lines in microprocessor. There are total 8 data lines in microprocessor. Now what we will do is that we will try to multiplex this lower order address line and make it as a data line. What we want is that we want to multiplex this lower order address line and mm, make it work as a data line. So we denote it as AD7. So we denote it as AD7 to AD0. A for address, D for data. It is doing multitasking because it will act as a address line as well as it will act as a data line at different occasions. Now see how it is done. So we told that, so I told you that the address of memory is 2060H. So this is our higher address. So higher address will get latched with, so higher address will get latched with our higher order address line. This higher order address line will have 20H. This higher order address line will have 20H, and this address will come to decoder. Easy. What I told you, this memory location is having address 2060H. This is our higher bit byte. So it will get latch with our higher order address bus, and it will then come to decoder. Now what will happen with 60H? This is lower order. So it will get latch with our lower order address line. It will get latch with our lower order address line. But what we have done is that we are using this lower order address line as data line also. That is, we are multiplexing it and we denoted it as AD7 to AD0. This is our AD7 to AD0. That is, now this 60H will get latched with AD7 to AD0. This 60H will get latched. This 60H will get latched with our AD7 and AD0. AD7 and AD0. That is, here in this portion, what we will have? We will have 60H. We will have 60H. Fine. So, microprocessor originated a memory address. Microprocessor originated a memory address that is 2060H, and this address is the address of memory location with which microprocessor wants to communicate. So 20H gets latched with higher order address bus, and 60H gets latched with lower order address bus. Lower order address bus is also used as a data bus, so we wrote it as AD7 to AD0. Now, as a microprocessor originated the address 2060H at the same time, ALE, that is address latch enable bit, also get high. Also get high. ALE will get high. ALE will get high and it will come to latch. When it will come to latch, then this high bit, that is 1 bit, will come to all the D flip-flops and it will energize all D flip-flop. See, what is the property of D flip-flop? That when the D flip-flops are energized, that is when we apply 1 to all the D flip-flops, then its next state will be equal to the data which is present in D flip-flop. So whenever D flip-flops get energized, then its next state becomes equal to the data which is present in D flip-flop. And when D flip-flop is de-energized, then it will restore its previous data. Then it will restore its previous data, and in that case you can write qn plus 1 is equal to qn, that where qn is our previous data. So what I told you is that first, the address was originated by microprocessor. At the same time, ALE bit was high. ALE bit was high. This high bit will come at latch. This high bit will energize all the D flip-flops. And D flip-flop has a property that when it get energized, then its next step, and then its next state is the data which is present in D flip-flop. So this 60H data which was present here, which was present at the inputs of all the D flip-flop, it will come to the output of all the D flip-flop, that is it will come to Qn plus 1th state, and this 60H will come here. See what we have at the output of D flip-flop? We are having A7 to A0. What is our A7 to A0? It is our lower order address bus. So we can see it here that 60H get latched to our higher order address bus. This is our higher byte, and the lower byte finally get latched with our lower order address bus. Earlier it was with AD7 and AD0. AD7, AD0 and A7, A0 is not different. It is just that with lower order address bus we are doing multiplexing, so we have noted it as AD7 and AD0. And here it is A7 and A0, that is this will only deal with addresses, but this will deal with addresses as well as with data. How it is dealing with data, that I will show you in a short while. So now this 20H was already present at decoder. Now this 60H will also come at the decoder. Now the decoder will give a single output and it will energize this memory location. This memory location will get energized. And as read bar was also energized from the microprocessor, this is a control signal, read bar is energized from microprocessor. So it is given command to the memory. It is given command that read operation has to take place, that is data which is present in memory location 2060H. Here this data will be read and it will be brought back to the microprocessor, and it will be brought back to the microprocessor using this path. Suppose data is suppose data is 20H. So now this 20H data which is inside this memory location will be read, and this 20H data will come back. This 20H data will come back to processor. See, I can write the direction of arrow. This direction will be in this side. This, this, this. This direction will be this side. This direction is this. This direction is this. Here, this. Here, this. Here, this. Now 20H is coming and this will go inside processor. So we can say that it is bidirectional. It is bidirectional. It is bidirectional. So you will say that, sir, earlier you told that AD7 to AD0 was having 60H, but now but now 20H is coming through this path. So 20H will override 60H. Yes, you are absolutely right. 20H will override 60H. 20H will override 60H, but and this 20H will come inside the processor, and our aim, which was to read 20H data from this memory location and bringing it back to processor, is complete. Our aim is complete. But see, um, by the time, as I told you, that ALE was energized, and after energizing all the diff flops, when the data 60H comes here, then ALE again becomes de-energized. Then ALE again becomes de-energized. Now here we saw that 20H is overwriting 60H. So what will happen to this data? This 60H data will remain same, and it will remain latched between A7 to A0. Why? Because my ALE is de-energized. My ALE is de-energized. So as my ALE is de-energized, it will de-energize all my D flip-flop. It will de-energize all my D flip-flops. And I told you earlier that in the de-energized state, what is the next state of a D flip-flop? It is the previous state. And our previous state is 60H. So this 60H will remain intact here. But here our data has changed from 60H to 20H. So it is clear. So see, here we can see higher order address bus, unidirectional. Okay. See, I told you this is our lower order address bus, unidirectional. But this AD7 to AD0, it is our data bus. It is our data bus. It is bidirectional because at one instant it is taking addresses, it is dealing with addresses, and it is taking addresses from microprocessor towards peripheral devices, and in next instant it is dealing with the data, it is bringing back data from peripheral devices to microprocessor. So it is a bidirectional. So it is bidirectional. So it is bidirectional. So I hope it is clear. If I again revise it, then I am saying that my aim is to bring data 20H, which is present at memory location 2060H, to the processor. So what processor will do? Processor will first originate address 20X H. It will first originate address 2060H. It will first originate address 2060H. This 20H will get latched with higher order address bus, and it will come to decoder. Simultaneously, ALE will get energized. This ALE will energize all my D flip-flops, and as a result, this 60H, which was latched with our AD7 and AD0, this 60H will come here. My 60H will come here at A7 and A0, and this 60H will come at decoder. Then my decoder will energize my memory location, and as control signal read is high, so this data 20H, which is inside memory, will be read, and it will come back to processor in this path. So my this path, that is AD7 to AD0, it is acting both way. If it is acting like a data address bus as well as a data bus. When this 20H is overwriting this 60H here, then this 60H will not be affected. This 60H will remain intact with our lower order address bus, because ALE is de-energized by this time, and as ALE is de-energized, all my D flops will also be de-energized, and it is property of flip flop D flip flop that when it is at a de-energized state, then its next state is the previous state. Its next state is the previous state. So this is how we are achieving multiplexing of address and data lines. So you can see that so interesting things are going inside the microprocessor, and how we are using this lower order address line and we are multiplexing it as a data line and address line. So this all was the working of microprocessor and how it is multiplexing address and data lines. So now you will say one thing, that sir, why we are doing all this multiplexing? Why we are doing all this multiplexing? It would have been better if we had used address line separate and data line separate. Our complete A15 to A0 would have worked as a address line at all instant, and we would have another 8 pins for data lines for as D7 to D0. Then see the problem was, at that time the testing bench available to test microprocessor could deal with only 40 pin microprocessor, could deal with only 40 pin microprocessor. That is the test bench which was available at that time. It was able to deal with only 40 pin microprocessor. It was able to deal with only 40 pin microprocessor. And if we would have used address line separate and data line separate, then we would have required 24 pins for achieving our purpose of address line as well as data lines. But by multiplexing lower order address line as data line, we are achieving the same function by using only 16 pin. So here we have saved our 8 pin. So here we have saved our 8 pin, and we have to do this saving because the test bench available at that time could deal with only 40 pin microprocessor. So that was the requirement for the multiplexing. So that was the requirement of multiplexing. So again, we are having higher order address bus A15 to A0, lower order address bus A7 to A0. This lower order address bus, we are multiplexing it as address bus as well as data bus, and we have denoted it as AD7 to AD0. Okay. And we can see here that we discussed earlier also that address bus is unidirectional. See, this part is acting purely as a address bus, it is unidirectional. This part is acting purely as a address bus, it is unidirectional. This part is acting as a data bus, because sometimes it deals with address, sometimes it deals with data, so it is bidirectional, which we discussed earlier also. So I think now after this much of explanation, it is clear to you that how we are doing multiplexing of address and data lines. What was the role of this latch? What was the role of this latch? This is an external module. This is an external module which is connected with the microprocessor. But we don't have any other option also other than connecting this external module with the microprocessor. because the test bench available at that time was of only 40 pins. So by using this latch module, which is having a number of D flip-flops, we are reducing our requirement of 24 pins to 16 pins by multiplexing this lower order address line. And from here we also saw the functionality of D flip-flop, that what will be the next state of D flip-flop when it is energized, and what will be the next state of D flip-flop when it is de-energized. And then we saw here that how 20H data of memory was overwritten 60H, but this overwriting is having no effect on the address which is saved in the low order address bus, that is A7 to A0. So I hope this part is clear to you. This is very important to understand the functionality of microprocessor and to understand the multiplexing of address and data lines. So now, after this discussion of multiplexing of address and data lines, we can conclude one important result. We can conclude one important result, and that is, if ALE pin, if ALE pin is high, if ALE pin is high, if ALE pin is high, then all 16 address line are acting like a address bus. All 16, all 16 address line, all 16 address line, all 16 address line are acting as address bus, are acting as address bus, are acting as address bus, are acting as address bus. And if ALE is 0, ALE1 means ALE is energized. And now if ALE is 0, if ALE pin is 0 or ALE is de-energized, then lower order address bus acts as a data bus. Lower order, lower order address bus, lower order address bus, lower order address bus acts as data bus. Lower order address bus acts as data bus. So this is an important conclusion which you should know. And by this, by energizing ALE and by de-energizing ALE, we are achieving multiplexing of address and data lines. So now we have seen that how we are doing multiplexing of address and data lines. Now we are doing one more multiplexing here. While doing memory read or memory write or input output read or input output write, we are doing one more multiplexing. We are doing one more multiplexing. So let's see. I told you earlier that microprocessor performs four basic function. Microprocessor performs microprocessor performs four basic function. Microprocessor performs four basic function. Microprocessor performs four basic function. One is memory read. One is one is one is memory read. One is memory read. Another is memory write. Another is memory write, then input output read, input output read, input output read, input output read, and input output write, input output write. See here, we are saying that input output read, it's a common terminology which we uses, but reading always takes place from input devices. So if we talk about input output read, it means that microprocessor is reading from input devices. And if we are talking about input output write, then it means that microprocessor is writing into output device. It is writing into output device. Microprocessor cannot read from output device, and microprocessor cannot write into input device. So keep this in mind. So in all the four basic functions, we can see that it is a kind of active low signals. It is a kind of active low signals. It is a kind of active low signals. Active low signals. That is in their output. If we have a 0 bit, that is in their, not in the output, in their input, when we will have 0 bit, then only this will be activated, then only this will be activated. Now see, we can see here that a microprocessor performs four basic functions. So for performing these four basic functions, we would have required 4 pins, but it is not like that. We can achieve these four basic functions. We can achieve these four basic functions by using only 3 pins. By using only 3 pins, and we can achieve it only because there's a very important concept that at a time microprocessor can perform only one function. This is very important. This is very important. At a time, microprocessor, at a time, microprocessor can perform only one function. Microprocessor can perform only one function. Only one function. At a time, microprocessor can perform only one function. Only thing is that microprocessor performs its function in such a high speed that it looks that it is doing parallel computing. It is performing 2 3 functions at a time, but it is not so. It can perform only one function at a time, and using this concept, we have multiplexed, we have introduced multiplexing concept, in which for performing 4 functions we have used only 3 pins, in which we have a multiplexed selection of input, output and memory through a single pin. Through a single pin we can select either input, output or memory, and here we are doing the multiplexing. And for multiplexing, we have to use external hardware. For multiplexing, we have to use external hardware, and the external hardware used is the NAND gate. External hardware used is the NAND gate. NAND gate has a property. NAND gate has a property that if these are the inputs, and this is the output, 0 0 0 1 1 0 1 1, then for 1 1 the output will be 0, and for the rest the output will be 1. We are interested with this 0. We are interested with this 0 because I discussed earlier also that all these functions, memory read, memory write, input output read, input output write, are active low signals. So we require 0 at their output. We require 0 at their output. Only then this will be activated. Only then this will be activated. Only then this will be activated. Now let see a table. Let's see a table, and then we will discuss different combinations. Then we will discuss different combinations. Then we will discuss different combinations. I will write it function. Function. First, let fill it 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. Then 0 means it is we are dealing with memory. 0 means we are dealing with memory. Now it is the 0, 0. That is, it is reading as well as writing. That is, this functions signifies that we are reading as well as writing from the memory at a same instant of time. So I told you earlier that it is not possible. Microprocessor cannot cannot perform two different functions at a time. So I can write it not possible, not possible, not possible. Now coming to here, again we are dealing with memory, and we are reading it. It is one that it is a write will be disabled. So it is a kind of memory read. It is a kind of memory read function. Now coming to this, it will be a kind of memory write function. It will be a kind of memory write function. Write function. Now this here it is 1 1, that is we microprocessor is neither reading nor writing. That is, here there is no operation. Here there is no operation. Here there is no operation. Now here again 0 0, that is not possible. If read bar write bar is 0 0, then the function will be not possible, and if read bar write bar is 1 1, then it means no operation. It means no operation. This will be not possible. Now here we are dealing with the input. Here 1, so we are dealing with input. So it will be input output read. It will be input output read. This will be input output write. This will be input output write. And here again 1 1, that is no operation. Here again 1 1, that is no operation. No operation. So this is the table. From this table, if we know the, we can conclude that if we know the inputs at this pins, then we can easily say that which function it is microprocessor is performing. Which function microprocessor is performing. So let's take one two examples. See, if we will, I told you that this NAND gates are external gates. NAND gates are external gates which we have to connect with the microprocessor to perform multiplexing, by which four functions of microprocessor can be dealt with 3 pins. So we can connect it like this. These are connected like this. These are connected like this. Now read bar, it will come here. Read bar, it will come here. Write bar will come here. Write bar will come here. Now let take one combination. Now let's discuss one combination 0 0 1. Let's discuss 0 0 1. Let's discuss 0 0 1. That is 0 0 1. 0 0 1, 0 0 1. It is 0, it is 0, and it is 1. It is 0. So let's see. Here we will have 0, and here we will have 0. It will become 1 1 1, and it will become 0. That is, we will get memory read. We will get memory read. Now coming to this, here 0 and here 1. Now it will be 0 will become 1 here, and 1 will become 0. It will be ANDed, so it will come it is 0 will become 1, and 1 will become 0, that it will become 0. And if we take again the inverter, then what we will get here? We will get here 1. We will get here 1. We will get here 1. So here there will be no operation because it is active low signal. So we require 0 for it to get activated. Now similarly, if you will continue it for remaining 2, then here and here also you will see that you will get 1 1. So from here also we can conclude that microprocessor at a time can perform a single function. Here if it is performing memory read, then all the remaining 3 functions are deactivated. So I hope this is clear. What I told you is that uh, we are doing multiplexing here also. We are doing multiplexing here also, in which through a single pin we are selecting input, output, and memory. So by doing this, what we are achieving is that all the 4 functions of microprocessor are dealt with 3 pin, and we don't require 4 pin for 4 functions. So we have saved one more pin here. So the problem which we had earlier, that the test bench has 40 pins, so we wanted to reduce the number of pins as far as possible. So here also there was reduction of 1 pin. Then we have to connect a NAND gate for it. For NAND gate, this all the 4 functions, memory read write, input output read write, are active low. So we want output 0 at the output of the NAND gate. And then we also discussed the different possibilities, where I told you that if it is 0 0 at read bar write bar, then it is not possible, and if it is 1 1, then it is no operation. Then it is no operation. And by taking this example of 0 0 1, we saw that only one function is performed by microprocessor at a time. So I hope this part is clear to you. Now coming to the discussion of memory. Here we will see what all components are interconnected to form a memory, and how memory works, how we fetch data from memory, and how we feed data into memory, and how this address lines are working, how this address lines are working, how this decoder is working, and what is the functionality of this input buffer, what is the functionality of this output buffer. We will look into it one by one. So we all know, let's start from this side. Let's start from the right hand side. Then we know that memory is a group of registers. 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 So suppose here we are having number of registers. Here we are having number of registers. Here we are having number of registers, and we further know that registers are group of flip-flops. 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 Okay, memory is group of registers. Registers are group of flip-flop. Then suppose each register is having 8 flip-flops. Suppose each register is having 8 flip-flop. Suppose each register is having 8 flip-flops. Suppose we are having total registers. Suppose total registers in a memory is 256. Suppose we are assuming it that total, suppose total registers in a memory, total registers in a memory is 256. Okay, and each register has 8 flip flop. Each registers each registers have 8 flip flop. Each registers have 8 flip flop. Then what will be the total capacity? Then what will be the total capacity of memory? Then what will be total capacity? Then what will be total capacity of memory? Total capacity of memory will be equal to 256 into 8 bits. 256 into 8 bits. We know 8 bits is equal to 1 byte. So we can write it as 256 byte. So we can write it as 256 byte. That is total memory. Total capacity of a memory is 256 byte if we are having total registers as 256 and each register is having 8 flip-flop. So we can vary the capacity of memory. For varying the capacity of memory, we have two options. Either we can increase or decrease total number of registers in a memory, or we can increase or decrease total number of flip-flops in each register. So we are having two possibility, or we are having two options to change total capacity of memory. First option is changing the number of registers. If we will increase or decrease number of registers, then our capacity will change of memory. And if we increase or decrease number of flip-flops in each registers, if we will increase or decrease number of flip-flops in each registers, then also the capacity of memory will change. We don't prefer this option. We don't prefer this option. We don't increase or decrease number of flip-flops in a registers, because we know that 8085 is a 8-bit microprocessor. 8085 is a 8-bit microprocessor. 8085 is a 8-bit microprocessor. 8085 is 8-bit microprocessor. So we generally keep 8 flip-flop in one register. So we generally keep 8 flip-flop in one register. So this is how we can calculate the capacity. This is how we can calculate the capacity of memory, considering it considering number of registers and number of flip-flops available in it. Number of registers and number of flip-flops available in it. Then we are having here input buffer. Then we are having here input buffer. What is the role? Whenever a microprocessor want to write data in a memory, whenever a microprocessor wants to write data in a memory, then data will not directly come inside the memory. It will get stored in this input buffer and then it will come inside the memory. Similarly, if microprocessor want to read data from memory, if microprocessor want to read data from memory, then the data which was present here, it will first come to output buffer and then it will go to microprocessor and then it will go to microprocessor. Here we are seeing that we are having two control signals. One is and one is read bar. One is read bar. one is the write bar, one is the write bar, and one is the read bar. So what will happen? The data will come from microprocessor, it will get stored in input buffer, and when this control signal write bar is activated, then data will come inside the memory. Similarly, when we are reading data from memory, then the data will first come from memory to this output buffer, and when microprocessor activates read bar signal, then the data will move from the output buffer to microprocessor. Here we can see that we are having two control signals, write bar and read bar. That is this memory we can say it as RAM. RAM is random access memory, that is we can read as well as write from the memory. That is we can read as well as write from the memory. If this control bit was not present, only this read bar was present, then we would have called it as ROM, that is read only memory. In that case we would have only read the data, but we couldn't write anything in the memory. So I think this part is clear. So I think this part is clear. Now see, coming to this decoder part, what is the functionality of a decoder? So I told you that the total capacity of microprocessor is 256 byte. So the input to decoder should have 8 data lines. Input of decoder, input of decoder, input of decoder, input of decoder, input of decoder will have 8 data lines, will have 8 data lines, will have 8 data lines. If we have increased this memory, if we have multiplied it by 2 and it has become 512 byte, then we would have required 9 data line at the input of decoder. Then we would have required 9 data line at the input of decoder. Means I am saying this, that this is not general. That I am saying that I am just taking an example. If I have taken A7 to A0 here, then doesn't mean that always we have A7 to A0. Sometimes we will find we can get A6 to A0, and sometimes we can get A9 to A0. And similarly, if we are having A15 to A8 here, then doesn't mean that always we will get this. This all things will vary depending upon the capacity of memory. So see, A7 and A0, what is this? These are our lower order address line. These are our lower order address line. So it has 8 lines. It has 8 lines. So it has 8 lines. So total combinations, what will be our total combination? Our total combinations will be 256. 2 to the power 8, that is 256. We have discussed this all in earlier lectures. And what will be its range? And what will be its range? Its range will be, if I talk about in hexadecimal, then it will be from 00H to FFH. 00F to FFH. Okay. So now suppose we are having so how this decoder works. Let's suppose how this decoder works. Suppose here we are having 0. Here we are having 0. That is our decoder will get energized. We will come here later part. Let us assume that here we are having 0. Here we are okay. Let's start from here only. Let's start from here only. See, this A15 to A8. This A15 to A8 is our higher order address line. Higher order address line. Okay. So to get output of NAND gate, as 0, we require A15 and A8 to be all 1. We require it to be all 1. We require it to be all 1. So when it will be all 1, then output of NAND gate will be 0. And in this case, decoder will get energized. Decoder will get energized. Decoder will get energized. See, if I take you little further, then you will correlate all this. See, what I discussed here also, that 20, we were having address 2060H. This is our higher byte. Higher byte get latched with higher order address line. higher order address line, and it directly comes to decoder. It directly comes to decoder. And this is our lower order, this is our lower byte 60H, and this 60H will come in our lower order address bus, that is A7 to A0. It will come from AD7 AD0. I told you how it is coming. But here just to see that our lower order address line is having lower byte address, that is 60H, and then it will come to decoder. So now you can easily correlate. So here this is our higher order address line. It will have a higher byte of address, and this is our lower order address line, and it will have lower order of address. The function of this is to energize or de-energize decoder. Function of this is to energize or de-energize the decoder, and function of this is to select memory locations. Function of this is to select memory locations. So how we are energizing, de-energizing? I told you that it is A15 and A8 and it is NAND gate, so we required all 1 year, then we will get 0 and it will get energized. Now how we will select address lines? Let's discuss here. Suppose we are having something A7 to A0, we are having something like this. We are having this bits. So what will be the role of decoder? Decoder will convert it into binary equivalent. Decoder will convert it into binary equivalent. Decoder will convert it into binary equivalent. So suppose it is 0 0 1 0 1 0 0 0. So it will be 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, 2 to the power 7. So what we will get? We will get 8 plus 32 means 40. So decimal equivalent of this input is 40. That is 40 number register will get activated. That is 40 number register will get activated or selected. That is 40 number register will get activated or selected, and from there we can either read or write data depending what control signal is available to us. So from there we can read and write data depending upon what control signal is available to us. So here this is our entire working of memory. This is our entire working of memory. I told you what is the working of this higher order address line. It is to energize, de-energize decoder, and here lower order address line, it is to select memory location. Decoder helps us in selecting memory locations by converting given input into decimal equivalent. Now I told you what was the function of input buffer and what was the function of output buffer, and how we can call it as RAM and how we can call it as ROM. So now if suppose anyone asks you that what will be the range, of this memory, before that let me show you one more thing. Before that, let me show you one more thing. See how memory are represented. See, this is the descriptive part. This is a descriptive part which I have showed you just for demonstrating and just for teaching you functions of different module. But in general, we don't represent memory like this. We represent memory like this. Here we will generally have enable pin. Here we will have enable pin. Here we will have a read pin if it is ROM, and here we will also have a write pin if it is RAM. Here we will have our A7 to A0. Here we will have A7 to A0, and here will be our, this is our low order address line, and here we will denote our data line, and here we will denote our data line. Here we will denote our data line. Here we will denote our data line. So this is the way, this is the way how we represent memory. So this is the way how we represent memory. Now suppose anyone asks you that what will be the range, what will be the range of this memory. So a range of memory we can vary. Range of memory we can vary. It is not dependent on microprocessor. It is dependent upon the external hardwares which we are connecting. It will depend upon arrangement of this. It will depend upon arrangement of this. How we are arranging it. How we are arranging it. What gates we are using here. What gates we are using here. And depending on that, our range will change. So if you are asked to find range, this is a very important question. This is a very important question for gate point of view. I am going to take number of questions based on this concept, and it is very important for gate point of view. Very important and very frequently asked questions in gate. So if you are asked to find the address, then what you will do? First, you will write all the address lines. First, you will write all the address line. A15, A14, A13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. See here, if we want to get a 0 at the output of NAND gate, then all this A15 to A8 has to be 1. It has to be 1. See, it has to be 1. It has to be 1. It has to be 1. Now this, see, now coming to low order address bus, I told you that it is 8-bit, so its range will differ from, its range will vary from 00 to FF. Its range will vary from 00 to FF. So what we will do it? We will take our first extreme, that is 00, and then we will take our last extreme, that is 1 1, that is 1 1. So these are our possibilities. So these are our possibility, and here we will always get all 1, because we want output of NAND gate to be 0. If here there would have been some other gate, or here there would have been some other arrangement. If suppose here we would have got a 0 here, inverter here, not 0, inverter, then everything would have changed. Then then the range of this memory would have changed. We will see all this. We will see all this in details when we will solve our questions. But here I am just showing you that what will be our approach while finding the range. So what will be its range? This is all 111, that is FF. This is all 00, FF00, H, and it will go from FF, FF, H. So this will be my range. So this will be my range. So what I told you is that range is not microprocessor dependent. Range is dependent upon the external hardwares and the arrangement of external hardwares which we are using, and along with it and based on it, our range of memory will change. So this was all about our arrangement of memory. So now we will take up some important questions on this memory and on this range concept. We will try to solve all previous year gate questions, and then you will see that how easily now you can solve these questions, and how easily you can find the range. So let's see the questions. Now, before coming to questions, let's see one another important concept where most of you get confused that what will be the result. Suppose we have four arrangement. Suppose we have four arrangement like this, like this, and in this it is given. I'm talking about the enable pin. Most of the time we get confused that when this pin will get activated and when it will not be activated. So what input you have to take for higher order address line or low order address line depending upon the questions. So we will have four arrangement here. Inverter is here. Here bar is on enable. Here we are having inverter as well as bar. Here we are having inverter as well as bar. And here we are having neither inverter nor bar. So see, if we are having an inverter, then it is active low. Then it is active low. Here, if we are not having inverter, but we have a bar over enable pin, then this is also active low. Then this is also active low. Here, if you are not having, if we are having neither inverter nor bar, then it is active high. It is active high. Active low means here input has to be 0 to get it activated. Here input has to be 0 to get it activated. Here input has to be 1 to get it activated. Now this is the disputed part. I will not say disputed part, but here most of you get confused. Here you see inverter and here you see bar, so you think that both will cancel each other, but it is not so. It is also another way of representing active low. It is also another way of representing active low, and it will get activated when we have 0 here. So I think this is clear to you. Now see. Let's solve a question. Let's solve a question. We have to find out range of this memory location. We have to find out range of this memory location. Now see, first if we want to discuss the properties of this memory. So here we can see that here we are having memory read as well as we are having memory write. Means here it must there must have been uh, read bar and here there must have been write bar. So by looking at this, we can say that we are talking about RAM. This is a RAM where we can read as well as write. Now coming to the capacity. Here see A7 to A0, A7 to A0, that is it is having capacity of 256 into 8 bits, or we can simply say 256 byte. This is the property. Now see, coming to the range. Now see, coming to the range. So first we will write this. Let's take another page. First we will write all this. A15, A14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. First, we will look into the low order address bus A7 to A0. So, let's draw a line here. So, its range will be from 00 to FF. So, first we will fill this 00 to FF. 00 to FF. Now, this part remains the most important thing where you have to apply your brain, and depending on this only the range of this memory changes. Now see what we are having. We are having A15 to A8 here, and we are having an inverter at A8. So what we have to get, we have to get 0 here. When we will get 0 here? We will get 0 here when at this, before this inverter, we have to get a 1, then only it will get inverted to 0. So we have to have 1 here. So to get 1, what all we require 1 1 here everywhere. A15 to A9 should be 1 1, and here we have to put 0, then only it will get inverted and it will become 1, and then here we will get 1, and here we will get 0. So I think this is clear. It is easy. So we will write it like this. At 8 we will get 0, and the rest will be 1. Rest will be 1. So now see the range. What will the range? It will be F, this 4, F, this, it is E, and then 0 0, this, and it will be F, E, F, F, H. This will be the range. So I told you earlier also that this defines the range. Any modification done here will change the range of the memory. So I think this is clear. It is easy. Now coming to another question. Let's solve another question. So here again we can see, here we are having a decoder. Here address line A15 to A12 are connected. Remaining A11 to A0 are connected. Means what will be the capacity of this? The capacity of this will be 2 to the power 12 into 8 bits, or it will be 2 to the power 12 bytes. We can write it like this also, 2 to the power 2 into 2 to the power 10 byte, and it will be 4 kilobyte. Memory is 4 kilobyte. Here we can see that we can do only memory read. Here we can do only memory read. So it is a kind of wrong. Read only memory. Okay. So now what it is saying, this address line is from A11 to A0. So its range will also vary from 00 FF. So we will see it later. Let's come to here. So to enable this decoder, we want 0 here. To enable this decoder, we want 0 here. So A15 will be 0. A15 will be 0. Then only it will get enabled here. Now, O0 is coming here. So to enable this, O0 has to be energized. To enable this, O0 has to be energized. So how can we energize O0? See, this is O0. Suppose this is O1, O2, and this will go on. O3, O4. So if we want to energize O0, so we will require 0, 0, 0 here. If we would have required to energize O1, then what we would have put? We would have put as 0, 0, 1. 0, 0, 1. It will go up to O8. It will go up to O8. Suppose this line would have continued from here. This line would have continued from here. Then here we would have got 1, 1, 1. 1, 1, 1. So this is simple. This all we have seen also in digital. This all we have seen also in digital. So I think that you can easily correlate. You will not get confused. Very simple, basic digital concepts. So we require O0. So we will have to put 0, 0, 0 here. If we would have required O8, then we would have put 1, 1, 1 here. So let's come to its range. Again, we will write A15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. A11. So this. So let's put 000 here. All will be our 0. Let's put 111 1 1. Okay. Then A15 to A, this all will be 0000000. So what will be the range? The range will be 00000 F, and it will be 0 F F F, not F. H will be H, 0 F F F. So this will be our range. This will be our range. This will be our range. So I hope this is clear to you. Only difference we are getting it here. We have used 3 cross 8 decoder. We have used 3 cross 8 decoder, and to energize it, or to activate this, we have to energize O naught, and for O naught we require 000. If here we would have got O for 8, then it would have 111. If it has if we want to if it has been connected by this O1, then we would have put it here 001. And A15 active low, so we require 0 here to get it energized. I hope this is simple to you. So these are some questions. So these are some questions which we have seen, and now I think that your concept must have been clear, that how we find memory locations, how we find memory locations. So now we will take another pattern of question which is generally asked in gate. Most of the time they give this type of questions, and then they try to play games with the mind of a student. So I will take that question also, so that everything will be clear for you. Now, coming to one more question based on finding the memory range. So here we are asked to find a memory range of these three memory. We are asked to find memory range of these three memory. Suppose I call this one as memory 1, I call this one as memory 2, and I call this one as memory 3. So we have to find memory range of this three memory. So see what all are given. Let's suppose we started from here. We have to find out it is a RAM or ROM. See, RD bar is given, that is, this one is ROM, read only memory, read only memory. If I talk about this, then here also RD bar, so this is also read only memory. Here we can find RD bar as well as WR bar, that is read in write in, both is possible. So this is our RAM, random access memory, random access memory. Okay. Now come in to the capacity of this memory. So here we can see that address line A12 to A0 are connected. A12 to A0 are connected. Means we can write it as 2 to the power 13, 2 to the power 13, and as each register is having 8 flip-flops. So this 2 to the power 13 into 8, we can write it as byte. We can write it as byte. And what it will become? It will become, this is not byte, this will be bits, because into 8 is there. Into 8 is there, so it will be bits. It will be bits. It will be bits. So finally it will come out to be 8 kilobyte. It will come out to be 8 kilobyte. I think now this all things are clear to you, but still I will explain you once more. 2 to the power 13 into 8 bits. If I will consider bits, and if I want to convert this bits into bytes, then I can say it is 2 to the power 13 bytes. 1 byte is equal to 8 bit. Then I can further break it into like this: 2 to the power 3 into 2 to the power 10 byte. 2 to the power 10 is kilobyte, and 2 to the power 3 it will come out to be 8 kilobyte. So I think now it is clear to you. So similarly, here also address line A12 to A0 are connected. So this will also be our 8 kilobyte. So this will also be our 8 kilobyte. Here A9 to A0 are connected, means 2 to the power 10 cross 8 bits. So it will come out to be 1 kilobyte. So it will come out to be 1 kilobyte. So I think up to now it is clear. See, this all things you are not asked to find, but still I am giving you an idea that how to read or understand properties of memory. It may come as an objective question. They may give you this block diagram of memory, and they may ask you that whether it is RAM or ROM, or they may ask you to find out its capacity. Our real problem, and that is to find the range. I will come in I will come to it in later part. So here we have data lines. Here we have data lines. Data lines will be D7 to D0, D7 to D0, D7 to D0, D7 to D0. Now here, this is our 3 cross 8 decoder. This is our 3 cross 8 decoder. At inputs, we are having A12, A11 and A10. A12, A11 and A10. Now its output is coming to this memory. So this memory will get enabled at O0. O0 means A12, A11, A10 will be my 000. Then this memory will be enabled. Now coming to this is also 3 cross 8 decoder, and here we are, the address lines are A15, A14, A13. Now its one output is coming to this memory. So this memory will be enabled when its output will be O0, that is input must be 000. And one output is coming to this decoder. So this decoder will get enabled when its output is O4. Its output is O4. So I write it like this: 000, 001, 010, 011, 100. See, this all I am writing for your ease to understand it. When we will do question, then we will not write all these basic steps. This must be kept in mind only. This is my 0, this is my 1, this is my 2, this is my 3, this is my 4. So to get O4, we require 100 here. Now similarly for O7, we will O7 will come here. That is, this memory will get energized when O7 will be my output. When O7 will be my output. When O7 will be my output. So this is the way that we understand a given question. First, we try to understand the arrangement which is given, and then we should proceed for the solution. Because if we start the solution first and then we start understanding the arrangement, then you will get confused and you will commit mistakes. So whenever a questions like this is given, where you have a very big architecture and connection, then you just understand that how everything's are connected and how everything's are connected, and then proceed. Then it will become very easy. Now see, it will become very easy. If we want to find the address, I will start with this one. I will first find the address of this third number memory, then second number memory, then first number memory. So see, I told you that if you want to find the address, then first write A15, all the address line, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Now see here, what are the address lines connected with this? A12 to A0. A12 to A0. So my A12 to A0, first write it as all 0 because the range starts with all 0, and then write all 1 because the range ends with all 1. Simple. Now see, this will be enabled when O7 of this decoder will be enabled. And when O7 will be enabled, when its input will be 111. When its input will be 111, then O7 line will get enabled, and this will come and it will enable this one. So write A15 to A14, 1 1 1 1 1 1. So this is my address range of memory number 3. Now you can find it in hexadecimal form. I am not going to do it, that you can do it easily. Now coming to the second one. Here also A12 to A0 are connected as address line. Suppose take the memory 2. So here also we will get all 0. Here also we will get all 1. Now coming to the main part. See, this will be enabled when O0 of this decoder will be enabled. And when this O0 will be enabled, when we will get 000 here, when we will get 000 here, when we will get 000 here. Now write 000 000. Now you will get the memory range of M2 also. Now coming to M1, let's see. M1, the number of address line is A9 to A0. So A9 to A0. So here I will write first all 0, and then I will write all 1. Then I will write all 1. Now see, this will be enabled when O0 of this decoder will be enabled. And this O0 will be enabled when we will have 000 here. We will have 000 here. We will have 000 here. Okay. So A12 to A10, 000, 000. Now see, this decoder will be enabled when O4 of this decoder is enabled. This decoder will be enabled when O4 of this decoder is enabled. When will O4 become enabled? When we will have 100 here. When we will have 100 here, 100 here. So write it here. 100, 100. Convert it into hexadecimal, you will get the answer. So this is the way you have to find the memory locations if there are more than one memory locations given. So they see this type of questions become so easy if you are able to understand first the architecture and the connection. These type of questions are very favorite for gate exams, and it is very scoring also. In gate you will not get this complete arrangement, you will get one or two, but in, yes, conventional you can get the complete arrangement. So I told you earlier also that first try to understand the arrangement, first try to understand the connections, first try to understand what the question is asking you, and then proceed for the solution, so that you will get right answers and you will not commit silly mistakes. So I hope this part is clear to you. Now we will discuss a very important concept, and that is fold back memory or mirror memory concept. Fold back memory or mirror memory concept. Let's see what it is. Many questions are asked in GATE exam based on this concept. So this is a favorite topic for GATE exam. So let's see what it is. So here also we have to find the memory range of this memory. We have to find memory range of this memory. This is a 3 cross 8 decoder. This is a 3 cross 8 decoder. This will be enabled when O2 is enabled. This will be enabled when O2 is enabled. So let's see how we can find its range. So for range, I told you first write all the address line A15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. This is all our addresses. Now see what it is in the memory. What are the address line connected at the input A10 to A0? Okay, A10 to A0. Put it all 0 here. Put it all 0 here. Then put all 1 here. Then put all 1 here. Easy. Then this will be enabled when O2 will be enabled. For enabling O2, what we require, this is A14, A12, and in mid there will be A13. So we know if we write the combinations as this 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So this is 0 1 2 3 4 5 6 7. So we want O2. O2, for O2 it has to be 0 1 0. It has to be 0 1 0. 0 1 0. 0 1 0. 0 1 0. Now A15, for enabling it, A15 has to be active low. So A15 will be 0 0. See, now all are completed. You will say that all are completed. Now we will find the range. No, all are not completed. See, A11. Do we have any information of A11? Do we have any information of A11 in this diagram? No, we don't have any information of A11 in this diagram. Then what we can do with A11? So if we are not given any information of A11, then A11 can take two values. Then A11 can take two values, either 0 or 1. We don't know which value it can take. So we are taking its two values, 0 and 1. So let's see. First we will start with 0. Let it is 0. Let it is 0. Okay, fine. Suppose here also I am just writing it for A11 because rest all will remain the same. Rest all will remain the same. I am only taking the A11. So I told you that if nothing is given of A11, then we will take A11 as either 0 or either 1, and we will get two different ranges for it. We will get two different range for it. So let me write it again, otherwise you will get confused. A15, 14, 13, 12, A11, 10, 9, 8, so 0. Okay. So now I told you A11 can take both value. It can take either 0 or either 1. So here I have taken 0. Now see, now try to find out the range. Now try to find out the range. So what will be its range? 0 0 0 0 0 0 0 1 0 0 1 0 0 1 2 2. Okay. If we take a pair of 4 4 4, if we take pair of 4 4 4, so its range will be 2 0 0 0, and here it will be 2, this will be 7, 0 triple 1 0 triple 1 will be 7, 2 7 F F. This will be the range, this will be the range, this will be the range when A11 has taken value 0. This will be the range when A11 has taken value 0. Now suppose if A11 has taken value 1, if A11 has taken value 1, so what will be our range here? This part will remain same. This part will remain same. Here also this part will remain same. This part will remain same. And in A11, I told you that A11 can take two value. It can take either 0 or 1. So 0 part we have covered here. So we have to take one part here. So now we have to find the range. So what will be its range? 0 0 1 0, again 2. 1 triple 0 means it will be 8 0 0 H, and this is a lower range, and the higher range will be 2 F F F H. So this will be the range. That is for this memory arrangement. That is for this memory arrangement. We are getting two range. For this memory arrangement, we are getting two range because nothing is mentioned of A11. Because nothing is mentioned of A11. So as nothing is mentioned of A11, so it can take either 0 or 1. So we have to find range once by considering 0 and then another one by considering 1. So this is the concept of fold back memory or mirror memory range. This is the concept of fold back memory or mirror memory range. Easy, I think you are able to understand it. Now suppose in this A11 was not given. Suppose you will get another question in which you will get A11 and A10 both are not given. A11 and A10 both are not given. So see what all combinations can be there. There can be, it can have either, it can take value either 0 0 or 0 1, 1 0 or 1 1. That is, there are four combinations. There are four combinations. When one was not given, when only A11 was not given, then there was two combinations. When two is not given, A11 and A10, when nothing is defined of the address line A11 and A10, then there are four combinations. 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 That is, there will be four range. We will get four range. We will get four range. And I think you can easily find out that how you can find the range. See, here A11 was not given, so we took here first we took 0 and then we took 1. Suppose A11 and A10 was not given here. Suppose A11 and A10 was not given here, then first we would have taken it as 0 0. Here 0 0. Okay, then we would have found the range. then we would have taken it as 0 1 0 1. Then we would have found the range. Then we would have taken it as 1 0 1 0. Then we would have found the range. Then we would have taken it as 1 0 1 0. No, not 1 0. Here we would have taken it as 1 1 1 1, and then we would have found the range. So we would have got 4 combinations and we would have got 4 range. Now if suppose we A11, A10 and A9 are not given, then what all combinations we will get here? We will get 8 combinations. We will get 8 combinations. We will get 8 combinations, that is we will get 8 range. That is we will get 8 range. So if I summarize it, then if 1 is missing, if 1 is missing, then it will be 2 to the power 1, 2 range. We will get 2 range. If 2 address lines are missing, if 2 address lines are missing, then number of combinations, then number of combinations will be 2 to the power 2, that is 4 combinations or 4 range. Similarly, if suppose n address lines are not given, then we will have 2 to the power n combinations and or 2 to the power n range. Then we would have 2 to the power n combinations or 2 to the power n range. Important. This is the concept of foldback memory or mirror memory range. That if we don't have any information of one address line, then we will get 2 to the power 1, that is 2 combinations or 2 range. If 2 address line is not given, then there will be 4 combinations, 4 range. If n address lines are not given, then we will get 2 to the power n combinations or n 2 to the power n range. Now here, so here this we got when A11 took value as 0, first one. So this is our main range. This is our main range, and this was the range when A11 took value, when A11 took value as 1. When A11 took value as 1. So this will be my fold back range. Fold back range or mirror range. This is my main memory range. This is my main memory range. This is my foldback memory range or mirror memory range or mirror memory range. Similarly, if I talk about this, then this first combination will be my main memory range. First combination will be my main memory range, and rest will be my fold back memory range. Then we will have fold back memory range. Similarly here, the first one we will call it as main memory range, and this we will call it as fold back memory range. So I think now it is clear. If you get such type of arrangement where some address lines are missing, then you should know that it's a concept of a foldback memory or mirror memory range. Then you have to proceed in this way. You have to find out the number of combinations which are possible which are possible with missing address lines, and then you will find that number of ranges. And then in the question, if it is asked that what will be the main memory range, then the first combination will be my main memory range. And if question in the question it is asked that what will be my foldback memory range, then the remaining ones will be my foldback memory range. So I think this concept is clear. Very important concept it is for gate point of view. Generally, they tend to give questions on this, and in that case, you will get more than one memory range. I hope this is clear to you. Now, coming to memory mapped input output. Now, coming to memory mapped input output. Let's see what happens here. So, here we can see we are having 16-bit addresses A15 to A0, 16-bit addresses A15 to A0 connected with NAND gate, and when its output will be 0, then this will be enabled. Then this will be enabled. So you will say that, sir, it's a 16-bit address. Sir, it's a 16-bit address, and here we have already written memory read. It means that this is a memory. This is a memory. But I will say no, this is not a memory. This is a input device. I will say this is not a memory. This is an input device. And I am enabling or activating this input device using 16-bit address using NAND gate. Can I do it? Why not? See, I have a input device. I have a input device. I just need to enable it. I just need to enable it. For enabling it, I have a two way. Either I can use a 8-bit address. Either I can use a 8-bit address, or I can use 16-bit address. Who can limit me? Only thing is that my ultimate aim is that my input device must get activated, and for activating it we can use either 8-bit address or we can use 16-bit address. Anything we can do, anything we can do. Okay, now it is clear. So I am saying that it's an input device, and I am enabling it with a 16-bit address, and I am enabling it with a 16-bit address. Okay, but microprocessor is not knowing that it is an input device. Microprocessor is not knowing it's an input device. Microprocessor will treat it as memory device only. See how? Suppose we have an instruction LDA 16-bit address, and let the address be FFFFH. We will look all these instructions in the coming session, but till now just you know that what is the meaning of LDA 16-bit address. It means that it states that load accumulator with data present at 16-bit address. Meaning of LDA 16-bit address is that load accumulator with the data present at 16-bit address. So when we give these instructions to microprocessor, then microprocessor understand that it has to communicate with a memory location. It has to communicate with a memory location, and no, it has to communicate with a memory. It has to communicate with a memory, and then further it has to pick data which is present at memory location FFFF of memory, at memory location FFFF of memory. So what microprocessor will do? Microprocessor will generate 16-bit address. FF will come at higher order address line, and this will come at A8. and combining this will this ff lower bits will come at lower order address line. So my this the input of NAND gate will have f f f f h. So its output will become 0, and this my input output device will get enabled. It is my input output device, but for microprocessor it's a memory, because I have given an instruction LDA. LDA means that it has to communicate with memory. Fine. So now it has to read data. So it has to read data from memory. So it will generate memory read control signal. It will generate a memory read control signal. So here we will get 001. When 001 will be activated, then this my control signals will get activated. My control signals will get activated. Now the data which is present inside the input device will get copied, and it will come back to the microprocessor. It will come back to the microprocessor. So see what I am saying. I am performing LDA operation. I am performing LDA operation. Meaning of LDA is that we have to load accumulator with the data which is present at 16-bit address. So if we will input this instruction to microprocessor, the microprocessor has to perform two things. It has to first generate 16-bit address. Here the address are generated, and then a microprocessor know that it has to communicate with a memory. So it will generate memory read control signal. But actually I have connected an input device here, and the data which we are copying, that data is copied from an input device. Now you will say that why we are doing it. You will say that let's suppose, we will come to it later. Suppose we have another instruction STA. STA. So STA means store data of accumulator in memory location FFFF. We have to store data of accumulator at this memory location. So in this also, microprocessor will first generate this memory address. Memory address will be generated, and then this time it has to perform memory write operation. This time it will perform memory write operation. This time it will perform memory write operation. So here we will get something like this. Here we will get something like this. Now memory write pin will be activated, and we can write data here. So this two functions are implemented. These two instructions are implemented. Now you will say that, sir, why we are doing it? Why we are doing it? Why we are fooling microprocessor by connecting input output devices? And this time when we will perform memory write operation, then it will become output device. It will become output device, not become it means that we have connected an output device, and we are fetching and we are feeding data to output device. So you will say that, sir, why we are doing it? Why we are fooling microprocessor by using instructions which are memory related, but actually connecting input output devices. So when we discussed peripheral mapped input output, so we saw that there was 8-bit address line. That is, microprocessor could generate 256 addresses, each for input and output. 256 addresses, each for input and output. Each for input and output. But by this arrangement, by using 16-bit address, microprocessor can generate 65536 addresses. 65536 addresses, each for input and output. Each for input and output. Understand it carefully. Each for input and output. So here the number of addresses which microprocessor could generate, or the number of memory locations or the number of input output devices with which microprocessor can communicate was only 256. But now here the number of input output devices with which microprocessor can communicate is 65536 devices. So this is the advantage of memory mapped input output. So this is the advantages of memory mapped input output. So this is the advantage of memory mapped input output. Now here we can see one more thing, that in a peripheral mapped input output, we were using control pins as input output read and input output write. But in memory mapped input output, the control signals which we are using is memory read and memory write and memory write. See, this all are objective questions. I will summarize it, but this all are objective questions which will come in your gate as well as in your ESE exam, or also in PSU's exams also. In gate you don't find much weightage of microprocessor, but in ESE and PSU you cannot even imagine of clearing those exams without microprocessor. See, earlier were the days when people used to skip microprocessor, still they used to get selected. It was around 10 to 12 years before. But at that time, the issue was that if one student is skipping microprocessor, then rest all are skipping microprocessor, because there was no one, not many good faculties who can teach microprocessor the way now you are taught. So if everyone is skipping microprocessor, then it doesn't affect the output. It doesn't affect the result, or it doesn't affect the cut off. Sorry. But now you cannot imagine of skipping it, because now everyone is studying microprocessor, and so study it nicely. See. Now coming to another concept of memory mapped input output. Let's see another and the last concept. After this, this topic of peripheral mapped input output and memory mapped input output will get over. Now suppose I am saying that this is my input device. This is my input device, but I am using 16-bit address and I am using a memory read control signal, and I will fetch data from input device, considering it to be a memory device. Considering it to be a memory device, that is, I will fool microprocessor using LDA operation that this is a memory device, but it is actually an input device. Similarly, here I will fool microprocessor that using STA instruction that this is memory device, but it is actually output device where we are using memory write control signals and using 16-bit addresses. And why we are doing it, I told you that the number of addresses will be or the number of input output devices with which we can communicate increases in memory map with respect as compared to peripheral map. So this is an memory mapped operation. This is memory mapped operation. This is also memory mapped operation. This is also memory mapped operation. Now see, come in here. This is my memory. And here I can a memory read as well as memory write. That is, it is a kind of RAM. It is a kind of random access memory. Now see what will happen. Suppose we have address FFFFH. Okay, we have address FFFFH. Now what microprocessor will do is that microprocessor is connected with this also. 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 That is FFFF. H will come here also, here also, here also. So first, if we will talk about this and this, then even if FFFFH is here, available here and available here, then also at a time both this input device or output device will not get activated because of this control signal. At a time we will either do memory read or we will either do memory write based upon the input to this control pins. So we can conclude from here that address of this input device and address of this output device can be same, which we have discussed earlier also, that 65536 addresses are generated for microprocessor, each for input device and output device. Now see what will happen here. Here also FFFFH is available here, higher bits in here, lower bits here. But here there will be a problem, because here we are having memory read also, memory write also. So there will be confusion that which one will be selected. This will be selected or this will be selected. So this confusion is eliminated by keeping one condition in mind, that memory addresses of input or output devices can never be same with the memory locations of uh, memory device. For suppose if with 2 to the power 16 combination we have 65536 addresses can be generated, 65536 addresses can be generated. And suppose if we have used 5536 address as memory, we have used 5536 address as memory, then the addresses available for input output device is only 60,000, is only 60,000. 60,000 address, 60,000 address is available for input output device, is available for input output. So what I am saying is that input device, memory of input device and memory of output device can be same, because we are differentiating input and output by memory read and memory write control signals. But address of input device or output device can never be same of that of memory device, otherwise there will be confusion that which one will be selected. So if we are using 5536 addresses as memory, then only 60,000 addresses are available for input and output device each, and not 65536 are available. So I hope this concept is also clear to you. So now let summarize some of the properties. Let's summarize some of the properties of memory mapped input output. Very important concepts I have told you. So just go through both peripheral and memory mapped again, and everything will be clear. So what I told you here, microprocessor will generate 16-bit address. It will generate 16-bit address. Second, memory read and memory write control signals are used here. Control signals are used here. Whereas in a peripheral, input output read and input output write were used. Here 65536 addresses are available, are available for input and output device respectively. This is the advantage of memory mapped with respect to peripheral mapped. With respect to peripheral mapped, here instructions used are SDA, LDA. There are other instructions also which are related with memory will come under memory map. But here STA and LDA, there we were using in and out. And here we can write one another thing, that memory address of input and output device can be same, but memory address of input output device and memory device can't be same, because then we cannot differentiate that which one will get activated. So see, this all are properties of memory mapped input output, and we have earlier seen the properties of peripheral mapped input output. So this was all important concept of both this mapping. So I think that it is clear to you. Now we will look into another important concept, and that is peripheral mapped input output, peripheral mapped input output, and memory mapped input output. This topic is also a favorite topic for GATE and ESE exams, in which you will get many theory questions based on this topic. And the problem is most of the students don't even have knowledge of these topics, and if they are having knowledge, then they have half cooked knowledge. So whenever they find a question based on peripheral mapped input output and memory mapped input output, then they generally tends to do a mistake. So here we will look both this peripheral mapped input output and memory mapped input output in details. We will look into all the properties of this both kind of types of input output mapping, and then all your doubt and queries will be resolved. So let's start. So first we will deal with peripheral mapped input output. First we will deal with peripheral mapped input output. In our previous discussion, we have seen we have seen it. Where we have seen it? We have seen it when the microprocessor was dealing with input output devices. When microprocessor was dealing with input output devices using in and out instructions, then there we saw peripheral mapped input output. But let's see it again. In details. So suppose microprocessor wants to communicate with a with an input device and read data from an input device So we discussed earlier also that for this we will use instruction in instruction. By using in instruction, microprocessor can read data of input device. And let's suppose we have an 8-bit address. Suppose we take it as in ffh in ffh. Then what is the meaning of this instruction? The meaning of this instruction is that microprocessor wants to read data which is present at memory location ffh in input device Okay, then let's see how it is done how it is done by macroprocessor. So it's an 8-bit address. So this 8-bit address will come here at AD7 and AD0. It will come here at AD7 and AD0. It is not a 16-bit address. The higher order address bus, there will nothing be at the higher order address bus. This address will come at AD7 to AD0. Then using this latch, this address will get latched here. This address will get latched here. This address will get latched at a lower order address bus A7 to A0. A7 to A0. Now see, this A7 to A0 is connected with this AND NAND gate through hard wire. This A7 to A0 is connected with a NAND gate through hard wired. So the output of this NAND gate will be 0, and this input device will get enabled. This input device will get enabled. This input device will get enabled. Here ALE is 1. Here ALE is here ALE is 1. Here ALE is 1. Now we have to give control signal also, so that we have to give a control signal also. So we have to read data from input device. We have to read data from input device. So we will have something like this: 1 0 1. So when 101 will be present at the control pins, then the input output read command will be activated. Input output read command will be activated, and now the data which is present at this memory at this input device, and at memory location 77H, and at memory location 77H, that will be read, and this data will come into the microprocessor through this path, and this data will come into the microprocessor through this path. Here the data will not coincide with 77H, with 77H, because by this time ALE has become 0. By this time ALE has become 0. So this data get latched at the output of latch module, and this data will come here and it will go here, because now this AD7 and AD0 is acting like a data line. So this is how a microprocessor reads data from input device. Now suppose we want to write data into output device. At output device. Now suppose we want to write data at output device, then see, again same thing will happen. First our ALE will be 1. Our ALE will be 1. So this 77H, which is at a lower order address line here, it will get latched with and it will come here, now this is connected with this NAND gate. And so its output will be 0, and now it is my output device. Now this is my output device, and output device will get activated. So now if we want to write data at the output device, then we use out instruction. For reading data we were using in instruction. For writing data into output device we will use out instruction. So what is the meaning of this instruction? Meaning of this instruction is that microprocessor wants to write data at a output device at a memory location FFH. So now this output device is activated, but now we want to write data into this. So the status of control signals will be something like this. It will be 110. So now our input output read control signal will get activated, and now the data which is at a microprocessor will come, and it will get stored in the output device using this path. Because now this AD7 and AD0 is acting like a data bus, and this low order address, that is 77H, is already latched here, because by this time ALE has changed from 1 to 0. ALE has changed from 1 to 0. Fine. So this was all about the concept of peripheral mapped input output. So this was all the concept of peripheral mapped input output, in which microprocessor is communicating with input device and output device, and how it is mapping and how it is mapping with input and output device is demonstrated here. So we talk about if we talk about the properties, so if we talk about some of the properties, so if we talk about some of the properties of so if we talk about some of the properties of peripheral mapped input device, so if we talk about some of the properties of peripheral mapped input output, then what will be it? So for first property, microprocessor, for peripheral mapped input output, microprocessor deals with 8-bit address. It deals with 8-bit address. It doesn't deal with 16-bit address. It deals with 8-bit address. Because for communicating with input output device, we only need 8-bit address. For communicating with memory, we required 16-bit address. Now second one is the two important instructions in peripheral mapped input output is in and out instruction. Two important instructions in peripheral mapped input output. Two important instructions in peripheral mapped input output are in and out instructions. The third property is that for peripheral mapped input output, microprocessor can generate 256 addresses, 256 addresses, 256 addresses separately for input and output device, separately for input and output device, for input and output device, for input and output device. See, um, we had 8-bit address. We had 8-bit address while dealing with peripheral mapped input output. So 2 to the power 8 is 256. So microprocessor can generate 256 addresses. Microprocessor can generate 256 addresses. Now see, we have two different control pin. We have two different control pin. One is the input write pin, and other is it's one is the input read pin and another is input write pin. That's why we can generate 256 separate addresses, 256 addresses, 256 address for input device, and 256 address and 256 address for output device, 256 address for input device, 256 address for output device. Suppose we had only one control pin, something like input output read write. It is just hypothetical. Don't remember it. In that case, if we would have used this pin only one control, if we had input output read control signal, and using this control signal we would have communicated with input as well as for output devices, then we would have got 256 total addresses for input output. We would have got 256 total addresses for input as well as for output, but here we have two separate control signals. So microprocessor can generate 256 separate address for input and 256 separate address for output. This is important, and this sort of questions are asked in exam. First, they will ask you that in peripheral mapped input output, 8-bit addresses or 16-bit addresses are used. So its answer will be 8-bit address. Then second question may be that what are the instructions used for peripheral mapped input output? They will give you in instruction, out instruction, STA, LDA. Then its answer will be in and out. Then third and the important one will be that in peripheral mapped input output, how many addresses a microprocessor can generate for input and output devices. Then we can say that it is 256 each, that is 512 in total. So this was all our properties of peripheral mapped input output. So now see another important concept we will see here. So I told you that for dealing with the input output device, we require only 8-bit address, and this 8-bit address get latched here, and then finally it comes at the lower order address line. So you will say that, sir, by this time, by all this process, what will happen to higher order address line? What will happen to higher order address line? Will it remain idle, or what data will be stored there, and what it will do? Yes. Then its answer is that during all this process, when the 77H was latched here, and then it was latched here, and then it came to this input output device, and everything was going on. This 77, the higher order address line, or we can say this 77H address, this 8-bit address 77H will also get copied, at this, that is at higher order address line, will also get copied, at this higher order address line, will also get copied, at higher order address line, Then see, from here we can discuss one important condition or concept also. So what I am saying is that if we are having an instruction in 77H, we are having an instruction in 77H, then this 77H address will also get copied at higher order address line. That is, we have an option that by connecting this higher order address line with this NAND gate, by connecting this higher order address line with this NAND gate, we can achieve the result which we were achieving by connecting lower order address line by this NAND gate. See, why can't we achieve it? If we get this address copied here, and in this NAND gate, if the manufacturer applies inputs A15 to A8 instead of A7 to A0, then again the same thing will come, again the same thing will happen. This 77H will enable this input device, and the control signals we are already having input output, right? So the data will come here, so the data will be read, and it will come here. So what will be the benefit of this? What will be the benefit of using higher order address line with while dealing with input output device instead of using lower order address line? And the benefit is that in this process we don't require latch. In this process we don't require latch. For enabling input output device, we can use higher order address line, and for bringing the data to microprocessor we can use this path, and this latch would have got bypassed. So for dealing with input output device, manufacturer has two way, that is that they can either use higher order address line in which latch get bypassed, and or we can use lower order address line in which latch is included, So This is another important concept of using peripheral mapped input output, which you should keep in mind. So see, by this concept, what I am telling you is that if I write it as A15 to A14, 13, 12, 11, 10, 9, 8, and here we will have A7, A6, 5, 4, 3, 2, 1, 0. So in this case, what I told you that in the first case, the address as at lower order address line was 77H. Okay, fine. 77H, so it will be 1111111. Then again I told you that we can that in microprocessor what it happens is that while dealing with input output device, this is address 77H also get copied to higher order address line. It means here also we are having the same thing. Here also we are having 77H. Here also we are having 77H. Here also we are having 77H. Okay, fine. Now see one interesting thing. Suppose this arrangement is given to you, and in this NAND gate, this all inputs are applied. This all inputs are applied. Okay, eight address lines, eight address line. So the input of NAND gate has this 8 address line, but here you can see that I have not used A15 to A8 in continuation, or I have not used A7 to A0 in continuation. I have used A15, then A14, then A5, then A12, then A3, then A10, then A1, and then A0. Then see, now if microprocessor wants to perform a input read operation, if it wants to perform input read operation, and if you are given an instruction like this, in again the same instruction in 77H, that is microprocessor wants to communicate with input device, and it wants to read data which is at memory location 77H of input. So if we give this inputs at the input of NAND gate, then will it work? Then will it work? Then will it work? Very important, very important. Listen to it carefully. Then will it work? I will say yes, it will work. See how? I told you that this 77H will come here, and this same address 77H will also get copied at higher order address line. Fine. Then here I am having A15, then A14, then ideally here we should have got A13, but I have written A5. See, what is value of A13? 1. What is value of A5? 1. So whether it will make any difference if I connect A13 address line or I connect A5 and address line? No, there will be no difference. Now again A12, okay, then I have connected A3. I have connected A3. Now see what is the value at A11 and A3. It is same. It is same. So will it make any difference if I connect A3 instead of A11? No, it will not make any difference. Then it is A10 and then A1 and A0. A1 and A0. See what is the value of at address line A9 and A8, and what is the value at address line A1 and A0. It is same. So will it make any difference? No, it will not make any difference. So this arrangement, it will work properly. Absolutely it will work, and we will get the desired result, and we will get the desired result. So these are the concepts which you should study, and you should have an hold on it, because in gate exam this type of concepts are only used, this type of questions are only framed in which if your concept is weak or not clear, then you will not be able to solve the question. See what question can be asked in gate exam. What questions can be asked in gate exam. In this architecture only, suppose one arrangement would have been given like this, one arrangement would have been given like this, in which the inputs at NAND gate would have been A15, 14, 5, 12, 3, 10, 1 and 0. And in another and you would have been given one another diagram in which they would have given the inputs of NAND gate like this: A15 to A8, and they would have given you another diagram, and they would have given the connections like this: A7 to A0, A7 to A0, A7 to A0, A7 to A0. Then they would have given you this instruction in 77H, and the question would have been asked was that in using which arrangement microprocessor can read data which is present at memory location 77H. Then most student would have suppose that this is option A, it is B and C, and options given are only A, only B, only C, only PC, only AC, and ABC. Means you will not get more than 4 options, but I am just taking it with what all possibilities can be there while framing the questions. So most of student would have ticked C, because they would have thought that microprocessor has to deal with input output device, and for dealing with input output device, we only need 8-bit address, and that 8-bit address will only come at this lower order address line, that is at A7 to A0. Then another set of student who had a concept slightly better than this, then they would have thought, no, this 7 address also gets copied with higher order address line, so A15 and A8, this will also work. But the students who know this concept, that what are the values at this and what are the values or at this, so if the values at this are same, then we can use any one of it, then those students will pick the answer as ABC. Those students will pick the answer as ABC. So this was all the concepts which I wanted to tell you regarding peripheral mapped input output. Regarding peripheral mapped input output, I also discussed with you that what type of questions can be asked in various exams. So I think now it is clear. Now I will discuss with you the memory mapped input output. Now I will discuss with you memory mapped input output. Now, when we have learned all the concepts, so let's take an example. So let's take an example and summarize everything. If you have missed any part, or if any concept is not clear in earlier portion, Then listen to this part nicely. I'm going to summarize all the concepts. So if anything is missing, then you can cover it up. You have one more option of covering it up. And after discussing this example, we will discuss one important concept, that is peripheral mapped input output and memory mapped input output. And that concept is dependent upon this summarization. So please listen to it carefully. So please listen to it carefully. So here I am going to again demonstrate you that how microprocessor communicates with memory and how microprocessor communicates with input-output devices. Input-output devices. So let first we will deal with memory. Here we are having two memory. This is the first memory. This is the second memory. Here we can see that in the first one, memory read operation is taking place. Here in the first one, memory read operation is taking place. And in the second memory, we can see that memory write operation is taking place. Memory write operation is taking place. So first, let's see what is the range of this to memory. First, see what is the range of this to memory. Suppose I keep everything same. Here also A7 to A0. Here also A7 to A0. And here it is A15 to A8. And here it is A15 to A8. And the output is coming through a NAND gate. Output is coming through a NAND gate. And it is active low. Chip select. Active low. Chip select. Then say what will be the range? What will be the range? What will be the range of both memory locations? What will be the range of both memory? What will be the range of both memory? It will be 0, 0, 1, 1. And here we will have all 1. Here we will have all 1. So it will be something like this. It will be something like this. It will be something like this. Or I can write it like this way also. FF 0, 0 to FF 1, 1. This is range of both memory. This is range of both memory because we are taking it same. Everything is same. The arrangement of address and the arrangement of data line is same in both this memory. Okay, fine. Now suppose microprocessor. Now suppose microprocessor wants to communicate. Now suppose microprocessor wants to communicate with memory location FF01H. It wants to communicate with memory location FF01H. Then see what will happen. I told you earlier that the higher byte, that the higher this I told you earlier that this higher bit, that this higher bits will come at a higher order address line. See, this address line is connected with this also, hardwired, and this address line is connected with this also. Let me draw it with another color. Yes. This address line is connected with this also. This higher order address bus is connected with this memory also. This higher order address bus is connected with this memory also. So I told you that the higher bit, that is FF, FF will come here, FF will come here, and FF will also come here. FF will also come here. Fine. Then simultaneously ALE will be energized. ALE will be my 1. ALE will be energized. That is, it will be 1. So now my lower bits. So my lower bits, which was earlier stored here. My lower bits, which was earlier stored here. My lower bits, which was earlier stored here, it will come here. It will come at A7 to A0. It will come at A7 to A0. It will come at A7 to A0. Okay, fine. Now this lower order address bus is connected with this. Lower order address bus is connected with this. And this lower order address bus is also connected with second memory. It is also connected with second memory through hardwired, through hardwired, through hardwired. Okay, fine. So now you will say that, sir, this FF01 address is in this memory also and in this memory also. So simultaneously both memory will get activated. So simultaneously both memory will get activated. So simultaneously both memory will get activated. No, it is not the case. It is not the case. Why? Suppose microprocessor, suppose that microprocessor wants to read. Suppose microprocessor wants to do read operation from memory. Suppose microprocessor wants to do read operation from memory. So what will be the status of control signals? What will be the status of control signals? Here it will be 0, it will be 0, and it will be 1. So by using 001, my memory read, uh, my memory read control signal will be activated. Only my memory read control signal will be activated. And see, here we are having memory read, here we are having memory read, but here we are having memory write. So it will get activated or it will get enabled, but it will remain disabled or deactivated. But it will remain disabled or deactivated. So see, here I am going to give you an important concept that while choosing memory, or I can write it like this, or while interfacing interfacing with memory, three things are important for a memory to get selected or not. Three things are important for a memory to get selected or not. Three things are important. Three things are important. Three things are important for a memory to get selected or not. Three things are important for a memory to get selected is or not. First is higher order address line. First is higher order address line. Second is lower order address line. Second is lower order address line. Third is control signal. Third is control signal. Third is control signal. Third is control signal. when the data or output of all these three will match according to our desired operation, when output of all these three will match as the as our desired operation, then only that memory will get selected, otherwise it will not get selected. Suppose if I talk about the higher order address, if I talk about the higher order address line, so here I told you that its address is FF, and here also its address is FF. Fine. Now I will delete it. Now suppose what I will do, suppose I put a inverter here. I put a inverter here. So what will be its address? Its address will become FE, and its address will become remain FF. So now for microprocessor whose higher order address bus is connected to this and this also through hardwired, but while interfacing, this will be disabled, and while interfacing, and if we want to interface with memory location FE, let lower bit be anything, let lower bit be anything, then microprocessor, then this memory will get activated and this memory will not be activated. Okay, fine, because my higher order address is different. Here it is FE, here it is FF, but we want to communicate with FE, okay. This is the first scenario. Now if I talk about the second scenario, suppose here we are having A7, here we are having A7 to A0, here we are having A7 to A0, here we are having A7 to A0, here also we are having A7 to A0 as a lower order address line, as a lower order address line, as a lower order address line, as lower order address line. Now suppose we would have got something like this. We would have got something like this. This would have become A6. This would have become A6. And this would have become A7. This would have become A7. So now see what would have happened. My higher order address as well as lower order address of this would have been completely different as compared to the higher order address as well as lower order address of this. So again, though the microprocessor is connected with both this memory through hardwire, but at a time only one memory would have been selected based upon the memory with which memory address with which microprocessor wants to communicate. Okay, now coming to the third one, coming to the control signals that we saw earlier also. Suppose everything would have been same, suppose everything would have been same, suppose everything would have been same, it would have been A15 to A8, and this also would have been A15 to A8, A15 to A8, and this is A7 to A0, and here also A7 to A0. Then in this case, the higher order as well as lower order would have been same. The higher order as well as lower order address would have been same, but still only one would have been activated because it will depend upon the control signal. That is, either we are doing memory read operation, or we want to do memory write operation, because microprocessor at a time can perform only one function. It cannot perform two functions, so both would never have been selected. Both would never have been selected. So I think that now the concept is further clear to you, and if there would have been any missing part in your concept, then you would have filled it up. So this is the way how microprocessor communicates with memory. Now, in the same way, if we want to see how microprocessor communicates with input-output device, How microprocessor communicates with input output device. So see, for while communicating with the memory, microprocessor generates a 16-bit address. But while communicating with input output device, only 8-bit address is required. Only 8-bit address is required. Only 8-bit address is required. Fine. Then see, suppose here what we are having, we are having two input output devices. Here we are having two input output devices. Here the addresses, low order address is A7 to A0. It is A7 to A0. So what will be, suppose what will be the range of this? What will be the range of this? This would be FF. If I take everything 1 year, it will be FFH, and similarly it would also be FFH. FFH. Okay, fine. Now microprocessor wants to read microprocessor wants to read data from memory location FFH. Microprocessor wants to read data sorry, not from memory location, but from input device having address FFH. Microprocessor wants to read data from a memory location FFH of input device. Microprocessor wants to read data of memory location FFH from a input device. So see, we are having two instructions in microprocessor. In instructions part, we are going to see everything in detail, but here I just want to show you this concept. So I want these two instructions. Suppose we have in FFH, this instruction means that microprocessor wants to read data which is present at 8-bit memory location FFH of the input device and bring it back to microprocessor. Similarly, while communicating with output device, there's a instruction out FFH. What is the meaning of this out FFH? Its meaning is that microprocessor wants to store data at memory location FFH of output device, of a output device. Fine. So first we will see in operation. So we microprocessor want to communicate with the memory location FFH. So it is having only 8 byte. So this FF will come here. 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 Now ALE will be energized. So this FF will come here. This FF will come here. Now this A7 to A0 is connected with this also, and this A7 to A0 is connected with this one also. But this will be activated, this will not be activated, because we want read operation. So if we want a read operation, then what will be the status of our control signals? The status will be 1 0 1. In this case, only input output read control signal will be activated, and it will remain deactivated, so it will not be selected. So now once it is activated, now the data will be read. And this data will come to the microprocessor from D7 to D0. It will come to microprocessor from D7 to D0, and following this path, it will go inside the microprocessor. It will go inside the microprocessor. There will not be interference of this data and FF, because by this time ALE is disabled. That is, ALE has become 0. So as ALE has become 0, this FF will remain latched here at the output. This FF will remain latched here at the output, and this data will come from here to here. Now, similarly, if we want to write data into a memory, if we want to perform out operation, if we want to perform out operation, then similarly, this low order address will come here. ALE will be enabled again. ALE again. ALE will be enabled again. ALE will be enabled. FF will come here. FF will come here also. FF will come here also, but this time this will not be activated because we want to perform memory read, memory read. So what will be the status of control signal? It will be 110. It will be 110. So this will get activated. Now this is activated. Now we want to write data into here. So the data from memory will follow this path. And it will come here. Again, there will be no interference of FF with the data coming out of microprocessor, because by this time ALE has become disabled. So this FF will get latched here, and this data following this path will come here, and it will get stored in our memory. So this I have given you one overview that how exactly microprocessor is interfacing with memory as well as input output device, input output device. So I think now everything is crystal clear to you, and you have understand all the concept of it. Now there are two important concepts related to memory mapping. So let's quickly cover these two concepts, and then we will move forward for instruction set. So first one is finding starting and ending address for memory chip. Suppose you are given a memory chip, you are given capacity of that memory chip, and then you are also given its starting address, and you are asked to find its ending address, or you are given the ending address and you are asked to find the starting address. This type of questions also becomes a part of memory mapping. So what we have to do for it? So there are two steps. So first take an example. We will understand this step through a example, because if we will take up this step, then you will not understand that what I am trying to tell you. So let us see this concept through an example. So see, here what it is given. Here it is given that we are having a ROM. We are having a ROM whose capacity is 4 KB. We are having a ROM whose capacity is 4 KB, and it is also given that starting address is 8C4EH. Starting address is 8C4EH, and we are asked to find the ending address. So see, what will be our approach? Step 1. Step 1 is to find number of address line. Step 1 is to find number of address line. We know the formula. 2 to the power n is equal to big N, where big N signifies the capacity, and small n indicates number of address line. So if we talk about this, then it will be 2 to the power n is equal to 4 kilobyte, So it will be 2 to the power 2 into 2 to the power 10 into 2 to the power 10 byte. So it will come out to be 2 to the power 12 byte. 2 to the power 12 byte. Therefore, n or number of address line is 12. N or number of address line is 12. Now coming to step 2. Now we will represent this number of address line with equivalent 1, with equivalent 1. That is, there are 12 address line. So we will write 12 times 1. We will write 12 times 1. If n would have been 13, then we would have written 13 times 1. Then we would have written 13 times 1. See what it is written in step 2. What it is written in step 2. See, this is our step 2. Put equivalent number of ones. See, first step is find number of address line according to the capacity of memory that we have found. That is n is equal to 12 for this question. Then second step is put equivalent number of ones as that of address line and find hexadecimal value. Put equivalent number of ones as that of address line and find hexadecimal value. So that's why we here n is equal to 12. So we are representing it or putting it with we are representing it with 12 equivalent ones. 12 equivalent ones. Now we have to convert it into hexadecimal. Now we have to convert it into hexadecimal. Now we have to convert it into hexadecimal. So what we will get? We will get it like F F F F F F. Okay. We have converted it into hexadecimal. Now see. Then add or subtract to get ending or starting address. Add or subtract to get ending or starting address. That is, here see what it is given. Here it is given starting address is this. We have to find ending address. We saw in memory mapping that the range always starts with 0. If n is 1, we have seen that if n was 1, if n was 1, then starting range was 0, ending range was 1. If n was 0, starting range was 0 and ending was 1 1. So it is always in increasing. So now if it is given that the starting address is this and we have to find ending address, means we have to add this. We have to add this equivalent, then only we will get the ending one, because ending will always be greater than the starting address. Similarly, if suppose you are given ending address and you are asked to find starting address, suppose you would have been given here that this is the ending address and we would have been asked the starting address, then we would have subtracted, this to get the starting address, because starting address is always lesser than the ending address. Fine. So here starting is given 8C4EH, 8C4EH, and here we have found it as FFF. It is of 16 bit, it is of 12 bits, so we will consider the remaining 4 bit as 0. Remaining 4 bit as 0. Now we have to add it. Now we have to add it to get the ending address, and on add-in we will get it like 9C 4DH. I am not going to solve it. You can solve it on your own. I am just directly writing the answer. This is my ending address. This is my ending address. This is my ending address. So it is simple. What we have done, first we have found number of address line. First we have found number of address line from the given capacity. Then we have represented that address line into equivalent 1. Then we converted it into hexadecimal. Then we had the starting address, so we added it to get the ending address. If this would have been our ending address, then we would have subtracted it to get it the starting address. Easy. Now see another question here. Find starting address. Okay. See here the capacity is given 4 KB. Here ending address is given. We have to find the starting address. See. So first we will find the number of address line. So here we will get 2 to the power n, 2 to the power 3 into 2 to the power 10 byte. So we will get n is equal to 13. Now we will represent it with equivalent one. So 13 1. Now we will convert it into hexadecimal. We will get f, we will get f, we will get f. Here we will consider 000. If nothing is there, then we will consider it as 000. So it will be 1. Now what it is given? It is given the ending address is this. So the ending address is this. Ending address is this. Now we have to subtract it to get the starting address. We have to subtract it. We have to subtract it to get the starting address. And we will get the answer. We will get the answer as 4a. I am not solving it. You can solve it. 4a 3ch. 4a 3ch. This is my starting address. This is my starting address. So it is easy. So it is easy. Just keep one trick in mind. Just keep one thing. Just keep one thing in mind. Just keep one thing is just keep one thing in mind. Just keep one thing in mind. That is always keep this capacity. Always keep this capacity. Just keep one thing in mind. Always keep this capacity in bytes. Always keep this capacity, memory capacity, in bytes. Always keep this memory capacity in byte. Don't convert it into bit. Don't convert it into bit. See how the gate examiner will try to trick you. Here it is given 4 kilobyte ROM, so it is okay. It is already in byte, and when we have converted, we have kept it in byte. In gate you will get an question where you will find capacity as like this. It will be given something like this. They will give you like this. They will give you right there like this. Here it will not be written anything, bit or byte, it will not be written, but we should know that this is in bit. We should know that this is in bit. So we will ignore this. It is not that while finding the address line, we will do 2 to the power 12 and 2 to the power 3. And finally, we will get 2 to the power 15. And we will say that n is 15. No, it is wrong. It is wrong. It is wrong. We will not convert it into bits. We will not convert it into bits. We will keep it in bytes only. We will keep it in bytes only. We will keep it in bytes only. So keep this trick in mind. Keep this trick in mind. Otherwise, you will commit mistake. So if it is given 2 to the power 12 into 8, then we will know that it is in bits. So we will consider only 2 to the power 12. Then n will become 12. Similarly here, if we are given like this, then they will give it like this, 2 to the power 13 into 8. Then we will ignore this. We will only take 2 to the power 13, that is n is equal to 13. So I can write it like this. Always keep memory capacity. Always keep memory capacity in bytes. Important. This is important while solving such type of questions. Rest part is easy. You will, if you will get confused, then you will get confused in this part only. So keep this in mind.